Hi, it's Dave. Welcome to episode 255. Today, I'm joined by James Douma. He is an expert in machine learning. He's been on my channel before, and he's been one of the great assets to the Tesla community in understanding Tesla's neural nets and also their approach with full self-driving. So today is the beginning of hopefully a few videos we're going to do probably once a week for the next few weeks. But today we wanted to get started to give people an update. And I wanted to learn what's going on with Tesla's full self-driving efforts. So James, I want to welcome you to the show again.
Thanks. Yeah, I'm looking forward to it. I had a lot of fun last time.
Awesome. Yeah, I got some great feedback. Tons of people said they learned a lot from our past interviews. Can you give us an update? I heard that you got some a look into the Tesla neural nets, how they've changed over time, but also what the current kind of full self-driving neural nets are doing. Can you kind of give us a breakdown of what you've learned? Actually, maybe take a step back. How did you get access to Tesla's neural nets, right? The full self-driving neural nets, and what have you been able to see, I guess, in that process?
Yeah, so there's a large community of Tesla hackers out there, and there's one that I've worked with, Very Green, who, along with other people, has been looking. They're very interested in what's going on inside the car, and they're mostly interested in things that aren't really autopilot related. There's all kinds of software in the cars, but one of the side effects of their investigations is that occasionally they get access to bits and pieces of the autopilot stuff. So starting a couple of years ago, Very Green would occasionally share this stuff with me, and I would just take a look at it from the neural networking standpoint. Other people in the hacker community are in a much better position to sort of understand the binaries, essentially what the human written code is doing. But I was really interested in the neural networks, and I asked if I could, what I could get access to. And they shared this stuff with me. And so we worked together to develop some techniques for analyzing these things and try to understand how they fit into the rest of the stuff that the car is doing. So most of what I look at is the neural network specific parts of autopilot. Now, there's a lot more to autopilot than just the neural networks, although that changes over time. The first version of the first autopilot had a lot more code and very, very little in the way of neural networks in it. And over time, that's expanded. So occasionally I'll get a look at a set of networks. It's not like they have continuous access to these things, but over the last couple of years, I've seen little snapshots of the neural network architectures. And so I've been able to kind of watch them evolve. And from the beginning, I was really interested in what technical approach they were taking to making, to basically solving this problem. How do you apply neural networks to the problem of self-driving? It's a really interesting thing. So I would, get the neural network architectures. That was the first thing that we can back it. So a neural network has a structure, which is you bring information into one end of the network, and then there's a very large number of connections between all of these neurons. And those connections, they define the way that information can flow through the neural network. Now, it doesn't tell us exactly what the neural network is doing, looking at the pattern, but it gives us you can look at the architecture and you can get a pretty good sense of the boundary of what the neural network is trying to do. The other thing is, we're at early enough stages in the development of neural networks that almost everything anybody uses is, it's one of a set of recipes that out there. Like, natural language processing systems, there's 4 or 5 recipes for them that they tend to go, and people mix and match those blocks. And in vision, there's been a few different recipes that have been used. Maybe a larger number in vision, but I could basically look at the shape of the architecture in Tesla's networks and then go look at like what's the state of the art for this particular architecture, like what are they able to achieve with a certain size network, how is what Tesla is doing different from what researchers are doing with these networks, and what might that say about what they're trying to do and what their capacities are and so forth. So from the beginning, I was looking at them from that standpoint. And up until FSD beta came out, there's a pretty solid, steady evolution. We could see the networks. they would get bigger. Occasionally, they would change the structure of the way they were doing the inputs. The system itself, I mean, you can think of it a couple different ways, but one way of thinking about it is that they have a vision network on each camera. And what that vision network does is it takes the video stream coming in from the camera, and it analyzes it, and then it produces a bunch of outputs for each camera. And the outputs might be, where are the stop signs in this frame, or where are the pedestrians in this frame, or where are the cars, or how far away are the cars that you can see, where are the stop lines, where are the markings, where are the curbs. So a single neural network, they started out with a small number of variables, but over time, as it's become more sophisticated, the number of variables that they get out of each camera has grown and grown and grown, and now there are like thousands of them, literally, that they're asking for all the networks. For some things, multiple cameras get used, and the data between the cameras kind of interacts. So these neural networks, they're outputting a bunch of these variables, and this is the stuff that, like, the part of the system that I look at mainly deals with. Now, there's more beyond this. Those outputs, like, if the front camera neural network one of its outputs is, where are all the pedestrians, right, in the frame, and so the output of that is like a frame with little boxes around where all the pedestrians are. Say that's what comes out. So another piece of code basically has to take that and make a decision on the basis of that, and presumably I call it the driving logic. There's a couple of layers to this. There's the sensors themselves, what comes out of them. And then what neural networks are doing is mostly perception, which is basically taking the raw sensor outputs and turning it into the kind of information that you could meaningfully use in a human written program. Like, for instance, where are the pedestrians, or where are the center lines, or where is the car located in the lane, things like that. And that's what I'm calling perception here, is basically taking the sensor input and turning it into something that's usable. After that, there's planning, which is, given these inputs, what actions should I be taking to pursue the goal that the car is trying to do? Like, if it's trying to drive down the street, or if it wants to make a right-hand turn, it has to basically decide, okay, what are the things I need to do from this point forward to achieve that goal? And then at the end, there's this layer called control, which is, it takes one action at a time, and then it gets the car to do that. So the control stuff is, it actually turns the steering wheel or activates the brakes. And so control is all written by people. The planning part is kind of a mix at this point, probably. I've seen some outputs from the cameras which are clearly intended for planning. They're not just what I'm seeing. The simplest one of those to sort of understand is, one of the things the neural networks do is they guess at a path through the scene that's ahead of it. So the car's almost always moving forward. So in addition to, here are the cars and here are the lane markings and that kind of stuff, the neural network makes a suggestion, and it draws this three-dimensional spline, which is just basically a curve with a couple of bends in it, through the scene ahead of it. And that's a recommendation for where the car probably wants to go. This is the neural network looking at this saying, this is probably the way forward, right? So on a curving road, the spline would follow the curve. If you're in a lane and there's a car ahead of you, the spline might go around that car, for instance. It'll make some suggestions along those lines. So that's a planning function. It's not just a sensing function. And there are other things going on that we can see in the camera networks that are planning related, but the overwhelming majority of stuff is just answering questions about what's the situation outside the car right now. So the cars have been doing that for a long time. Over time, we've seen the networks get bigger, and there have been more variables. Some of the variables get broken up into small. You can tell that as they bump into problems in the development of particular features, they'll add additional variables to help them refine, their understanding of some phenomenon that they're trying to, break down in a way that's easier for the code that decides what the car is going to do to basically understand stuff. Okay, so we saw a really big change when it went to full self-driving, which is, well, first of all, the networks got a lot bigger. there were a lot more networks, and they were a lot bigger than they were before. Now, when a neural network gets bigger, that basically means you're applying a lot more processing to the input, to which you might be doing because you're trying to generate more outputs. But a lot of times you just want better accuracy. So the bigger a neural network is, and the more you train it on, and the more computation you spend on a particular neural network, the higher the accuracy of the output could be. So the outputs in neural networks, they're inherently probabilistic. So when it gives you that little screen and it's telling you where the pedestrians are, it's drawing little boxes where it thinks it sees pedestrians. And each one of them has a probability associated with it. And so, it might say, I think there's a 60% probability there's a pedestrian here, and I think there's a 90% here, or a 95. Of course, what you want is for the neural network to be as close to perfectly accurate as possible, especially when it's a really important question. And the bigger you make the network and the more training data, the more accurate those numbers will become. So it'll get those numbers, those probabilities will get a lot closer to 99%. And you won't see a lot of 50, 60, 70% things, because that's a problem for the people writing the code. Like, what do you do if the car says, I think there's a 60% chance there's a pedestrian in front of you, right? Do you brake or do you not? Well, probably you have to brake. Well, 40% of the time, assuming the probability is accurate, you're going to be braking and there's nothing there, right? So you want the probabilities to get closer to 100% and 0% as the choices, because that makes the programming easier. And it also means that you're going to have fewer, overreactions or underreactions that the vehicle does. And the bigger you make the network and the more data you train it on, the closer you get to that ideal of perfection, of always seeing a pedestrian when they're there, always seeing the lane markings exactly right, and so on. So that's one thing we saw, is we see more networks and we see them get a lot bigger. Now, previously I described it as if there was one neural network per camera. And, in the early days, there was one neural network per camera. When they were running on the GP106, the NVIDIA GPU, they had a limited amount of processing power. So they didn't have the luxury of being able to run like completely independent networks on every camera for the purpose of getting different kinds of things. And now what we see is they do run multiple networks on different cameras. And probably the networks are somewhat context dependent. Like, they might switch networks depending on whether they're stopped at a light or driving on a highway or trying to maneuver through an intersection or something. But we also see the networks get kind of specialized, like they're networks that are looking for moving objects, right? Because the moving objects have certain things in common. And if you build a network that just looks at moving objects, they can, there's certain, for instance, the time domain aspects of that kind of stuff are important. Then there might be another network for static objects, which is to say things that aren't moving relative to the road. So like stop signs and trees and the road itself and, curbs, they don't move. So you might have another network that does that. And so we see a proliferation of networks where a single camera might have 2, 3, 4 or more networks that all run on, and all these networks run in real time. So
James, I'm wondering, what's the state of camera fusion? Are these cameras being fused together into one view right now? And then are the neural nets being applied to that fusion view, or is it still being applied to individual cameras?
So they have a fusion architecture where they take a bunch of cameras. So the individual networks are still producing the outputs that they used to, but they're also producing these. They also have a really big output that feeds into a common network that basically brings all these cameras together to create like a single fused view of that. And then the fused networks go into a bird's eye view sort of network after that. And what the bird's eye view network does is it asks the car to imagine what would the world look like if I were looking down on the car from a great height? Like, give me a map of the car and its surroundings. So when you look at the display in the car, like if you've watched the FSD videos, there's a display. So that's pretty close to what's coming out of the bird's eye view networks if you were to look straight down. So it will, for instance, if you're driving down a road, the bird's eye network would show the curb next to you, and it would show, things that were maybe in the median or on the sidewalk next to you, and things on the other side of them also. The bird's eye network, it'll also guess. For instance, if you're driving past a wall, or if you're driving past another car, the bird's eye network doesn't, when what's on the other side of the car is occluded, the car can't actually see what's on the other side of the car. It'll guess based on what it sees in front of and behind the car. Like if it sees a curb go, extending past a car, it'll guess that the curb is extending through. And this is the bird's eye network is basically it's asked to bring together the top-down view from all these different cameras to synthesize a unified view. And it's also asked to guess about the things that you can't see, which is, and you can see this on some of the full self-driving videos where, it'll guess sometimes incorrectly about things that it can't see. So when the vehicle's driving past an obstacle, the things on the far side of the obstacle, they might vary. Or you might see a pedestrian will walk behind a car, and then the network will guess that the pedestrian continues for a little while, and then the pedestrian will vanish because at some point the car's not, the AP is no longer sure if the pedestrian still, like maybe the pedestrian stopped walking, or maybe they turned and they went some other way. So the bird's eye networks also incorporate time. That is, so the camera networks all come together to basically create a unified view of one frame, and that those get fed into the bird's eye network, and then the bird's eye network it also looks back over multiple frames. Now, so this is something that get pretty hard to see in the networks just by the nature of how this stuff goes. So I don't get to see a lot of it, but Karpathy's talked a number of times about this. He had a really good talk last February at Scaled ML, where he talked in some significant amount of detail about the architecture they were using in the vision networks and how they were doing the bird's eye networks. So everything I've seen is consistent with what he talked about. So my sense is that what he talked about on Scaled ML a year ago is a pretty accurate representation of what they're doing in the car. So anyway, the short answer to your question, like the networks got a lot bigger. They added a lot of this bird's eye top-down stuff to the systems, and they've added temporal integration. So they're looking across time in addition to just static frames.
How do you think the full self-driving software is integrating this bird's eye view with the individual camera view? So for example, the bird's eye view, it seems like it's giving kind of a broader view, but then you also have this forward-facing view, let's say, right? The main view of the forward-facing cameras. So let's say something is happening where, you're going through a turn, there's some type of obstacle. The forward-facing camera sees that obstacle. The bird's eye view might see something a little bit different, or I don't know what, but how does the software reconcile those two different views, and what priority does it give?
Okay, so the bird's eye view is a product. The car, of course, it can't see down from the top. It's got no way of directly perceiving that. So bird's eye view, it accomplishes kind of two independent things. One of them is that it's a way of asking the car to reconcile all the different cameras, right? Because if you're looking down from, like, no individual camera can see everything around the car from the top. So if you're going to generate a bird's eye view, essentially you got a little square map and the car's in the center. That's one way of asking the neural network to fuse all the camera views. Because, the front camera looks forward and the other cameras look to the side. And if you ask it, okay, now put all that together and ask me what the whole picture looks like. With a neural network, you can train neural networks to take almost any kind of input and generate almost any kind of output. But you have to have a way of asking a question that's relevant so that you're challenging the network to come up, so that when you train it, the thing you're training it to do makes sense in the context of what you're trying to accomplish. And so in that sense, one of the things, and maybe the most important thing the bird's eye view network approach does, is it asks the car to synthesize, to basically put everything together into a picture that makes sense. You're asking a question that forces it to reconcile the multiple overlapping camera views, right? Because if you don't challenge it to do that, it won't learn to do it. It's always going to take the easy way out. It's going to learn to do whatever the simplest thing is that answers your question. So you want to ask a question that's the simplest question you can ask, that at least includes the thing you want. And if what you want is to integrate all the camera views into kind of a holistic understanding of what the car's environment is, one thing you can do is, what would it look like? Ask the network, given all these camera inputs, what do you think it would look like if I was looking down on the car? So they're asking that question, and that's something they can answer. They can take map stuff. Essentially, they have a certain amount of bird's eye information so that they can determine a ground truth and provide an error function to feedback to the network to challenge it to get better at these. So that's one thing. The other thing that a bird's eye network does is that the bird's eye view does is it's a domain that's easy to write software in. So imagine that you have to write the software to control the car, right? Well, if I have a camera view forward and you've got a pedestrian in front of the car, well, you have to guess how far the pedestrian is. I mean, just having a pedestrian in front of the car isn't sufficient to make a decision about what you should do. Like maybe you're driving on a curve and that pedestrian's on a sidewalk, right? When you ask the neural network to create a bird's eye view, you're also generating an output that's an easy output for a programmer to write rules on, right? Because a programmer can basically look at the bird's eye output and he can say, okay, tell me where the road is. So here's the road. And you can ask the question, well, is this pedestrian in the road or are they not on the road? It's not like, are they in front of me or not? Once you've asked the neural network to create this map of the environment, now your programmers have a map to work with to make decisions about how they want to control the car. So you're getting two things out of the bird's eye network. One of them is you're getting a straightforward framework for fusing all these cameras together to get a kind of holistic view of asking the network to reconcile what it sees on different cameras. And then you're also getting an output that's actually useful because the people who are writing the planning code and the dynamic control code, they now have a representation that they can work with that's easy framework for a human programmer to work with rules inside. So that's why. So bird's eye networks they're a very clever solution to that. Like you could imagine another thing, and something that I thought that they were doing was I imagined it that they were trying to make a full three-dimensional sort of. I mean, the world is three-dimensional, right? A vehicle that's in front of you, it has a height, a width, and a depth, and it occupies some position relative to you. And so, as a human being, when you're sitting in a driver's seat and you see another vehicle, you have this sense of that thing in space out ahead of you, that you're in a volume of space. And because that's a simple and accurate representation of the reality that we're in, it's a good framework to be able to understand everything in it and to work in. But the thing is, it's really challenging if the simplest thing you're asking the neural network to give you is this completely all-encompassing depth, width, everything description of the world. If you ask for that, and if you challenge a neural network to do that, eventually it'll be able to do it. But it's not the simplest thing you can ask that forces it to figure that out. Just asking it, well, what would this scene look like from a different perspective than I am? That also requires a neural network to understand that the world is three-dimensional and these other objects occupy space separate from the vehicle. Because remember, a neural network, it doesn't know any of this stuff. It's a complete blank slate. It doesn't even know what a child knows when you start with it. Every single little aspect of what it learns about reality is something it has to figure out from the data that you're giving it. So you have to ask it questions that challenge it to come up with simple and powerful representations of the world that you can also build on to write to control the vehicle, right? So getting a neural network to understand that the world is three-dimensional is actually really challenging. We're giving it a bunch of 2D images, a bunch of them, right? And it's, they're 2D projections onto a 3D world, but it's got to make decisions in 3D. And somehow we have to stimulate it to understand that it's looking at a three-dimensional world, right? It's not looking at 4 or 5 dimensions. I guess it's 4 in a sense. It's a moving three-dimensional world. And that's not at all obvious, in the way that we build the neural networks. We have to challenge them to figure that out. And the bird's eye view is a simple, very clever solution to stimulating the network to figure that out. Because, you only have a bird's eye view in a three-dimensional universe, right?
Sure. I'm wondering, have you noticed that for the planning, let's say module or the planning code in in full self-driving, are they relying more and more on the bird's eye view for planning? Because before the bird's eye view, you didn't have that. So you're relying more on just the camera view, right? Are you seeing a shift over to more planning on the bird's eye view at all?
So I'm mostly looking at neural network architectures, and what I have to infer what they're doing based on the outputs that the bird's eye view outputs are going to be a lot easier to work with than the field of view outputs are. So I'm sure that they're making very heavy use of that. One of the things that we see in the evolution of these things over time is they don't. Tesla, I always expected, when they had a new piece of capability come out, that we were going to see this discontinuous change in how they were doing things, and it's never really been that way. They add new networks, they gradually transform the old ones, they consolidate old ones. I haven't seen them really get rid of anything. So they still have all the outputs that they had before. And my guess is that when the people writing the planning code suddenly had bird's eye top-down stuff, they didn't immediately abandon the way that they'd been doing stuff. They started integrating it into the way that they were doing planning. And over time, they'll probably rely more and more on it as they know they can trust it and they figure out how to use it effectively. And then gradually the ways they were using the field of view or POV representations will just kind of gradually go by the wayside. But bird's eye view is super powerful, and the integration, they get the 4D stuff. They were in 2D before, where they had snapshots, and now they're challenging the system to understand that it's a 3D world. And bird's eye, I think, is an important component of how they're doing that. And they're asking the world to understand that things evolve over time. Like if you see multiple frames in a row, and you see, if a block is traveling through a scene and it's labeled truck and it's, 90%, 90%, 90%, 80%, 90%, you see it 5 frames in a row. Well, you can be a lot more confident that that truck is actually there if you see it in multiple frames, right? And so little variations in the probability don't affect your confidence that it's actually a truck, as they do if you have to make decisions based on a single snapshot.
With bird's eye view, I mean, this is pretty interesting stuff here. How do they train that? I mean, how do you test and train? Like, for example, I understand, like, for more stationary objects, the neural net will output, different boxes or identify different objects, a cat, a car, a truck, etc., a moving person. And then you could train it. You could say, you could show them the correct things, and you could go back and perhaps correct the incorrect object, etc., to make the neural net improve. But with the bird's eye view, do you think some type of training is going on in terms of correcting maybe incorrect type of things, and how is that training being done?
Yeah, so it's not nearly as straightforward as training. If you just show me where the pedestrians are in this photo. Like, if I have a bunch of photos and I draw boxes around all the photos, I can challenge a neural network, just, give me this output. Like, here's a pedestrian, draw a box around it. And so I have a bunch of pictures with pedestrians. It's pretty straightforward. But if I ask the neural network, like, show me a top-down view and now put boxes around all the pedestrians, that's a lot harder. So, so you can do a certain amount of labeling by pulling in other sources that are naturally top down, as maps, for instance, are top down. So, but this is where it starts getting really interesting. So you can try to synthesize a true top down view of the environment. And this is when Elon was talking about video labeling and using Dojo to train in video. So so you can do this, and the way that it works is you have a car drive through a scene, right? You capture all the output from all the cameras, the accelerometers, all the other sensors, and that kind of stuff. You take all the footage from all those cameras, you put it in Dojo, you put it in a really big computer, right? And that computer walks that data back and forth and figures out what the ground truth must be. And you don't have to use neural networks to do this. You can use geometric priors and other sort of more straightforward, just geometric analysis to figure out what the three-dimensional scene must be in that situation. Then you can have a human being look at that three-dimensional scene on a computer in 3D and say, this is a pedestrian, this is a fire hydrant, these are the lane lines and that kind of stuff. Once the computer's got those labels, it can go back to all the frames that were used to make that scene, and it can label all of those inputs. And it can tell you, because it's got the whole 3D scene that's built, if I was looking straight down on the car from the top, this is what I would see at each instant in time. So you can do all this processing, and you can create this three-dimensional model of the thing. Then you can automatically generate all the labels that you need for training not just the cameras, but also the bird's eye. And then you can use that when you're at those as the labels for training the neural networks that you expect to do this in real time. So for instance, Dojo can do a bunch of geometric backend work on a stream of data where it knows exactly what happened from the beginning to the end, and it can go back and forth over it a bunch of times and throw a lot of computation at it and eventually figure out what the 3D scene is and generate all the labels. What the car has to do is it has to do this in real time as it's driving through it, right? So we're training a neural network to, on the flash, figure out what Dojo can do with a great deal of computation in the back end. And then, so Dojo can go figure out all this stuff to create the labels, and then we challenge the neural network to do this on the fly while it's driving. So that's one way of doing it. Mm-hmm. There's another technique, which Karpathy also talked about in scaled ML, which is self-supervised training. And in self-supervised training, you do a thing where you challenge a neural network to tell you what a scene looks like from one camera when it's seen from another camera, or you challenge a neural network to tell you, say that the car is driving down a road at 30 miles an hour, right? And you look out one of the side cameras at the side of the road and you see a scene. Now, the cameras take 36 frames a second. So 1/36th of a second forward in time, the scene will have shifted slightly. And I can ask the neural network, tell me what the next frame looks like, right, from that. So that's another way that you can do it, is you can ask the neural network to predict what a different camera would see or what it will see at some point in the future. So those techniques, they're called self-supervised because nobody has to label the data. The system supervises itself. It generates its own inputs. Now, the inputs you're testing against aren't quite as meaningful to a programmer because I'm not asking it, tell me where the pedestrians are that you're seeing out the side camera. I'm asking it, tell me what the camera will see in 3 milliseconds in the future or 30 milliseconds in the future. But the thing is, in order to be able to do that trick of predicting what it's going to see a moment in the future or predicting what another camera will see at the same moment in time, it has to figure out a lot of stuff about what the scene really looks like. And so that's a different trick that you can use. It produces kind of different outputs, but it'll give you some of the geometric understanding of the scene, which the bird's eye view also requires, and which the bird's eye view uses in a different way. So these things kind of work together. There's no, when Tesla started doing this, you could just do scene labeling and you could just ask it where the pedestrians were in the frame because the goals. But as the systems become more complicated and they're looking for greater and greater levels of accuracy and more nuanced understanding of, like, an important thing when you're driving down the road is what's that pedestrian going to do? So you see a pedestrian standing at a curb. This is a big problem in San Francisco. And you drive down the street in San Francisco, you're constantly driving about 2 feet from a bunch of pedestrians. And there's a lot of difference to how you behave with a pedestrian who's walking along the sidewalk towards you and one who's looking at their phone standing on a curb and you're wondering if they're going to step out in front of you, right? So eventually the neural networks are all going to have to understand all that stuff too. They're going to have to be able to read the body language and pose and motions of pedestrians as well as other vehicles and cyclists and that kind of stuff so that they can predict what that person's going to do and take appropriate action. In San Francisco, if you tried to drive someplace and you had the car stop every time it was within 2 feet of a pedestrian because it wasn't safe, you'd never get anywhere, right? You have to be able to predict what pedestrians are doing. And that's a pretty hard challenge. So as the challenges that the network needs to, as the predictions become more and more challenging, we have to get more and more clever and not just ask it one way of getting the data, but ask it a bunch of different ways. So now eventually when they've got Dojo working and they can really throw a lot of computer power at this, they'll be able to do a lot of that drive-through scene video, three-dimensional labeling, back propagate, all that stuff. But that's really computationally intensive.
So I want to ask you about this. So um, correct me if I'm wrong in how I understand this, but with video labeling, so let's say my Model 3 goes through a scene, and right now it's using the neural nets in my car to identify objects, giving it to planning and then control. But with Dojo, let's say we take that video kind of scene, we give it to Dojo. Dojo takes it through a supercomputer, does a crazy amount of computation. Doesn't necessarily have to be neural net or machine learning, but it could be geometric as well, and comes up with pretty much a 3D picture of that scene. And then a human labeler can go through that 3D picture scene, label the key objects, the car moving through, the person crossing the street, the dog going whatever there. And then we can basically take those labels and then train back the neural nets so that neural nets are more accurate in how they perceive that scene. So we're basically using the 3D constructing through Dojo to create a more accurate picture, let's say, of the environment, using that as we label it, but then using that to train the neural nets in the car. So in a sense, you're giving these neural nets like superpower, meaning they're on a different level now because they're using what Dojo has constructed as the environment. But if you do this millions and tens of millions over scenes, you train the neural nets in the car to basically identify the object as good as what, let's say, Dojo would do, you're giving your cars an immense amount of increased accuracy in terms of their neural nets. Is that kind of the gist of kind of Dojo and video training?
Yeah, you get a lot more accuracy, right? Because you're going to have a lot more data that's a lot more accurately labeled. So that's one thing that you get out of it. But another thing that you get is if I just label the pictures and I'm just asking it, okay, tell me, a human says this is where all the pedestrians are, and I give the unmarked image to a neural network, and okay, you tell me where the pedestrians are, right? And then I compare that to reality. I compare that to what the human said, and I generate an error function that I propagate back to improve the network. But one of the things you can't do with that approach is I can't ask the system to imagine something that's not in the frame and require it to do a good job of doing that, right? But when we start fusing the networks together and we build the whole three-dimensional scene, I can start asking it I've got a pedestrian that walked behind an occlusion, a tree, a bus, or something like that. And I want the neural network to understand that the pedestrian is still there. It's still walking along. I can ask it to imagine that the pedestrian is there, even though I don't have a picture to label, right? So Dojo can build the whole three-dimensional scene, including objects that are temporarily occluded. And I can ask the neural network, tell me what's behind that bus right now, or tell me what's behind that car. Because if it's a moving object, a human will know this. Right? Something, if you see a car parked across the street from you and another car transitions through the intersection, you understand that when the car's in the intersection in front of you, the other car's still at the stoplight on the other side, right? Like humans know that. But neural networks trained the simple way, they don't know that. But with the Dojo approach, I can do that because I'm asking the neural network to tell me the whole three-dimensional scene, including the stuff it can't see right now. Exactly. And so that so we get this. I was super excited the first time I saw the full self-driving videos, and you could see that the network was labeling stuff it couldn't see on the other side of obstacles because we were giving them imagination.
Yeah. So, I mean, to rephrase this, so with the whole 3D creation through Dojo, you're basically mapping these objects and where they're going to be, right, in the future, where they're headed in a sense, right, or predicting, well, I guess you're seeing where they're headed through that whole scene, but then teaching the neural nets that movement, I guess, right? You're teaching them how to see ahead.
So that's the next step, right? Uh-huh. So there's understanding the situation instantaneously, which might include, that's where the car is right now, and here's its velocity. Like that's also an instantaneous thing, that the vehicle has a velocity. Another thing is, tell me where it's going to be, in 100 milliseconds or 200 milliseconds. Like, where is that car going to be when I'm 50 feet forward, right? That's another level beyond what we're talking about right now. And they are doing that already. I mean, you can already see in the FSD videos that the car behaves differently. Like if it approaches an intersection and there's a cyclist coming, it behaves very differently than if the cyclist is stopped at the side of the road. Like it's there's already evidence that AP is looking at a scene and it's predicting what the various dynamic objects in the scene are going to do and responding to that. So some amount of that. And in the long run, it has to be really good at that. We expect that of humans, right? If you're going to pull out in front of another car, you need to have a sense of where that car is going to be when you get done accelerating up to speed. Like, is my path going to cross that other car's path at any point in the future if I do this maneuver? So you have to be able to project both your path forward into the future and the other thing, and understand if there's going to be any undesirable interaction there.
Interesting. Elon Musk was saying that video auto labeling is the holy grail. What does he mean by that?
So the thing I was describing before, where you have a car drive through a scene, you take all the data that comes off of the car, you stuff that into Dojo, and so Dojo recreates the 3D scene, right? You can auto label probably almost all that stuff. Dojo also has access to these trained neural networks of the previous version of the car, right? So it can run through that scene with those networks, and it can do a first pass guess at where all the stop signs and that kind of stuff are. And as the networks get better, it's going to be doing a really good job of that, right? It's going to be 99.999% right. So the human labeler's job, right now, when they first build Dojo and they're first building these scenes, he'll have to label a lot of stuff. There will be a lot of details that Dojo isn't getting right. But as it gets better, it'll be able to build this three-dimensional scene and pre-label thousands of things in the scene. And then the human labeler's job will be mostly just verifying that Dojo's right? And of course, at the tail end of that, you don't even need a human in the loop, right? All the cars out there driving, you can get all the snips from them. They can go into Dojo. Dojo can create vast volumes of labeling data, and then you feed that into the neural networks, and you close the loop with fewer humans in the process. Okay. Right now, they're labeler limited, right? They've only got so many labelers, and it's really labor intensive.
With video labeling, is part of the whole auto labeling where, because you can, let's say, use all your neural nets to identify different objects, because it's over time, there might be some frames where, for example, you're unsure, but because Dojo is reconstructed as 3D over time, then let's say it's 99%, it drops to 80%. But then Dojo knows that that's not 80% because it knows that object is really that object, right, in the beginning and the end. So then it is able to label at a higher accuracy or higher conviction rate, right, than just, without that construction.
So when Dojo's labeling, it also knows the future, right? Because Dojo's got the whole clip, the whole 10 or 15 seconds. So it knows what the pedestrian was doing in the future after your car passed the bus and looked back and saw the pedestrian was there, right? So whereas the neural network on the fly, obviously you don't know the future, you can't, right? But, Dojo gets a whole complete thing, can run it backwards and forwards and figure out what model of, what three-dimensional dynamic model of that scene is most consistent with what all the sensors saw all the way through the scene from beginning to end. And then we ask the neural network at any point in time to guess at the things it doesn't know. And eventually, like people, it'll get good at those guesses.
Exactly. It sounds like eventually using this model, the neural nets in the car will drive as good as potentially Dojo could drive, right? Because that's the data that you're training these neural nets with. Is that kind of the essence or the goal?
Well, Dojo can't drive because Dojo.
Sure.
At least not only is it too big to fit in your trunk,
but at least perceiving it could perceive the world. At least the important objects as well as what Dojo could perceive through its 3D rendering.
There are certain things it'll get really good at. Well, for instance, say you have a pedestrian walk behind a bus, right? And, so you imagine the pedestrian keeps walking, but maybe the pedestrian stopped. You can't know. There's an inherent sort of uncertainty to that, right? Dojo can know what the pedestrian ultimately did because, it knows, it'll know after it drove past the car that the pedestrian did in fact emerge from the back of the bus. And, the pedestrian's movement was consistent with walking. So then Dojo knows what the pedestrian must have been doing when they were occluded by the bus. Of course, the car will never be able to do that because it just can't know the future. So there are certain things that Dojo will know about scenes that the car can't know. All the car can do is make a good guess about that. But then that's just a limitation of reality. The car, the networks will eventually get really, really good at predicting the things which can be predicted. But, there will always be things that can't be predicted.
Got it.
I mean, you don't know if the pedestrian tripped behind the bus and fell over, right? That's just hard to predict.
How much of this effort do you think is like Tesla is already doing right now at this moment, which is kind of creating 3D scenes using that as training? Is that something that they're venturing into right now, or is this something they're kind of waiting for until they get Dojo really up and running?
So this is me reading tea leaves from what Elon has said. My sense is that they're building the infrastructure to do that, and it'll be a work in progress for a long time. To some extent, to make the commitment to build Dojo, you have to have already done a dry run on a bunch of this stuff so that you have some expectation of what results you're going to get. Neural network technologies are new enough that anything that you want to do, anything you want to do that's pretty complicated, there's a pretty good chance nobody's done it before. And because neural networks, they're very empirical. It's not a theory-driven domain right now. We have theories about neural networks and why they do what they do, and they're not very good. So you can't use a theory to predict, well, if I build a neural network, 3 times bigger, and I give it this data, and I include this other data at the same time, well, now what will my accuracy be? We can't do that. What we do is we build a rough sketch, and we test the idea to see if it makes sense. So I think that a couple of years ago, when people at Tesla were thinking about making Dojo, they were looking at the trend, and they were saying, well, a really big computer is going to be really useful. We're going to build a really big computer. Well, how are we going to use it? Well, if you want to make decisions about how you're going to use it, you do a couple of rough sketches of that, right? Like, well, what if we built 3D environments? Could we label the data? Would that be useful? And you can build a prototype that might be crude, and you might only have but the prototype will help you understand the benefit of doing it. So I think they did that, and they've probably got fairly sophisticated prototypes now, and they're probably building their way up the stack. Their tools are going to constantly get better, right? So I think the tools aren't one or two key features. They're thousands of small features that make the labelers more productive and that improve the quality and quantity of the output that you have available for training the networks. And I think that's just going to, AP is not going to be a product like a toaster where it's just done one day, right? Oh, there, toast bread. Okay, let's move on to the next product. We have this super lofty goal of making the system so superhuman that nobody ever dies, right? That is just arbitrarily good. And that's pretty far away. So, it'll get better at different kinds of situations, and it'll just keep getting better and better and better for a long time. And all the way along that, every single tool in their arsenal, they'll keep refining as they go. So I think that they've probably already prototyped tools that they won't be using in production for 5 years or 3 years or something like that. And they have other tools that they've been using for a long time that they're still refining.
This approach of using 3D or even adding time 4D to or recreate this and use it to backpropagate, train your neural nets. Like, how cutting edge is this? Like, are other people, other companies doing stuff like this? Is there anyone else doing this at scale? Let's say, what's your take?
I don't think there's anybody doing what Tesla's doing at Tesla scale, right? I think Tesla's there are certainly other people who train neural networks and use lots and lots of labeled data. And there are companies that are in the business of just making labeling tools that are basically, you have your 500 labelers, and here's a tool that they can sit down at their desk and it'll make them productive and help them avoid errors. So, there's a market for those tools. There are plenty of companies that are doing that. I kind of doubt anybody else is doing it at the scale that Tesla is doing it right now. Like, I think they probably are building most of the tools that they're using because probably none of the commercial tools that are out there can handle the scale that they're working at. So yes and no. Other people are doing it. I don't think anybody's doing it at the same scale that they are.
Got it. Do you foresee Tesla's Dojo supercomputer getting like? I mean, you're talking about this as a progression, right? There's probably no, point where everything's turned on. But do you think by the end of this year, Tesla Dojo will be like enough up and running in some form or fashion that it will make a significant difference to full self-driving and how accurate it is?
Yeah. So where is Dojo right now, and how? I mean, I feel like they probably could have Dojo Silicon, the first cut of Dojo Silicon done, but Dojo is more than just. I mean, they have a silicon chip they want to make that supports a particular computational architecture that they want. And Elon's already talked about the numerical format that they want to use, which is a numerical format that nobody else builds in silicon. So, they're building their own silicon to do this. But to build a system at scale that uses lots and lots of these chips requires a lot of power design, a lot of cooling design. Communications is for these kinds of things is very complicated, and it takes a lot of work to get the communication networks to tie all these things together to build a big machine. And that is a bigger effort than making the silicon. On the other hand, you can start using the silicon, if they've got their first version of their chip, they can run off 1,000 of those, put them on motherboards, go in the back room and pull a Google and, use a bunch of Lego blocks or just a regular, computer racks and get that thing working. And they'll want to do that to start understanding how these things work together and verify that the chip works and that kind of stuff. Is that Dojo? Or, I think their aspirations are high enough. Like they want enough sophistication out of this thing, but there's a good chance that they haven't built a full up Dojo at this point, like a full rack of the final design, but they have early versions. At what point do they have enough computation? Is Dojo enough computation that it's moving the needle on what they need? Because at the end of the day, Dojo is a way for them to cost effectively get the computation that they need in order to do this stuff. My guess is that right now they can probably buy so much computation that the hardware that they've built probably isn't moving the needle on it. Will they do that this year? Maybe. If they wanted to, they could. I don't know if they'll have a final version of Dojo. Maybe they'll have Dojo 0.9. They'll have a first up data center on Dojo 0.9 by the end of the year. When they get to where they start scaling Dojo, then I think it'll matter. Like they'll very quickly get to a point where Dojo, like my guess is, it drops their cost of computation by an order of magnitude, like out of the gate. So as soon as they get it for the same amount of money they're spending, they get 10 times as much back-end processing, and that'll move the dial on it for them when they get that. Maybe that'll be this year. I don't know.
Yeah, actually, there's Elon Musk replied on January 9th to someone said, will Dojo be able to do 1 exaflop FP16 sustained or peak compute? And could Tesla do a gigacasting day or Dojo day? That would be very exciting and informative. And then Elon replied, maybe a Tesla AI day later this year. So I talked to you earlier. I said maybe Tesla would do a Dojo day. I guess it's a Tesla AI day that Elon is referring to, and he might show Dojo by later this year, maybe by the end of the year. Maybe they might have something, I don't know what you're saying, like maybe something up. Maybe it might not be a full, version, but something to show.
I'm sure
people.
They've built at least a rack of it at this point. But Tesla can rent a good chunk of a data center right now just for doing back-end processing if they want to, or they can go out and buy, stacks of NVIDIA boxes and build a small data center and they probably use enough compute that it makes sense for them to build their own data center. You only really want to use the cloud if your duty cycle, like the fraction of time you use the hardware, is less than maybe 20% or something. Beyond that, it makes more sense to build your own. But they've only got so much money to spend on that. Although they've got a lot more money now than they had a year ago. So that might also be a moving target, right? True. The amount of money that they've got to spend on this.
Yeah. James, what I wanted to hear is, last time, see, I'm always tempted to go like 5 or 6 hours with you, just straight. I do an all day conversation, but I understand people like to sometimes digest it in chunks. And so what we'll do is we'll kind of wrap up here. I think this has been a fascinating first type of, just step into some of the current state of Tesla full self-driving neural nets. Next week, I'm fascinated by some of these other topics that you've shared just with me privately about the role of full self-driving with valuing Tesla and how analysts still aren't really valuing autonomy perhaps correctly or underestimating in the future, what that means as an investor. I'm super curious to know about that. I'm actually wanting to ask you more technical questions about any timeline guesses, or even I want your current thoughts on Lidar, if Tesla is ever going to use it, you think, or if it's just, not just practical.
No.
You're thinking it's not practical at all, Lidar?
No, I don't think they need more sensors, and I don't. Yeah. If they want to get superhuman, I think, they've got what they need. At that scaled ML, I should get you to put a link in the show notes of the scaled ML talk that Karpathy did a year ago. Because if you're really interested in the technical stuff, and a lot of what he's talking about will probably be over the heads of many people who are interested in this stuff. But you can look at the pictures and you can get a good understanding of what they're accomplishing by using neural networks the way they are. Anyway, he shows the pseudo lidar output that they generate. So in order to encourage the neural network to sort of understand depth as a component of what it's looking at, one of the things you can do is you can ask it, tell me how far away every pixel is in this scene that I'm showing you. So this is something that generating depth maps of scenes it's something that neural networks have been doing for a while now, right? And so he shows some of the depth maps they generate. They do in FSD, the networks, I went looking for where they were using depth, where they were generating what I think Karpathy called it pseudo lidar, which is basically, here's a picture, tell me what lidar would see in this picture. Well, if you can do that really well, what do you need lidar for, right? Essentially, if the neural network can look at a scene and it understands depth really well from looking at the scene, then the lidar sensor doesn't get you anything. And pseudo lidar is getting really good, right? So without having to spend all the money on the sensor or clean bugs off of your $100,000 emitter on the front of the car or any of that kind of stuff.
True.
So I don't think they're ever going to use it.
Okay, cool.
I think there's no way.
In another episode, I want to ask you about competition. Like, is there competition? What are the threats to, for example, Tesla's full self-driving aspirations 5, 10, 15 years down the road? So lots of cool questions. And then later on, I want to field a ton of questions that people have, and just really drill down on 20 or 30 questions or something for people. But I'm looking forward to chatting with you more next week and then the following week. And I'm super excited. I think Tesla autonomy has got to be one of the most exciting developments for this decade. It's monumental, and I think
it's the most interesting. SpaceX is doing amazing things. There's a lot of Elon's companies are doing amazing things, but looking back, my favorite metaphor of this thing is thinking about the Wright brothers, like about how the world changed around that. There's so many really interesting parallels, and one of the ones I love is how nobody believed that they were flying, and even when they were flying, people would go out and look at it, and photos were printed in newspapers for years afterwards, and people didn't believe it was actually doing it because you just get baked into this idea that something is really hard. And I think autonomous driving is in that space right now, where even people who are really steeped in it, it seems so far away. Right. It's such a hard problem, and we've been working on it for so long, and the goal seems to recede almost as fast as we approach it. And there's going to be this moment when it's not like that anymore. And I think that day is getting really close now, and the world is going to be very different afterwards.
Yeah. Is it just me? It seems like 2021 is like a very important year for Tesla full self-driving. It seems like it's going to be a year where there's going to be lots of improvements. Obviously, it won't be the end state by the end of the year, but it seems like this is going to be an interesting year, definitely, to watch. I'm sure the next few years too, but
we're in a window where things are happening really fast.
Yeah.
Yeah.
This is another thought. Have you ever thought about this idea where, like, it seems like Elon Musk, when he started Tesla, it was really electric cars. If you look at, the whole first master plan, there wasn't really autonomous driving at all in his idea, right? It was purely just electric cars. And it seems like such a serendipitous, like, moment of fortune, of good luck in some ways, where all of the technology for machine learning, but also vision, perception, all this stuff just intersects with Tesla's kind of rise as an electric car maker, where now they're able to not just ride the electric car wave, but now they're able to ride this bigger, maybe even bigger wave of autonomous driving. And they're just in the right place at the right time, but then they made certain key decisions to prioritize it and to really try to go for it, and they didn't try to mess it up. They're just like, hey, this is huge. We're going to embrace the opportunity.
The decision to like put sensors on all the cars before they had the software.
Exactly.
I mean, because it's thousands of dollars and it's a very non-trivial amount of risk and complexity that they're adding to the vehicles to put all those sensors on all those cars years before the capability had come into its fruition. I mean, obviously they get lots of value from it. I use autopilot a lot. Like, I don't even want to go anywhere on a highway without autopilot anymore. And it's not full self-driving, but man, it's so useful. But even so, that the autopilot isn't multiplying the value of your car by 5 right now, and it will, right? It will. That Tesla makes, the margins on their cars right now are like 20% or something. They make this $50,000 car and they make $10,000 on it or something like that. Like, that margin could be $300,000. Like, the value that autopilot adds when you get that, it's a huge multiplier on what Tesla gets to keep from that. So yeah, it changes the economics of the company, but it changes the economics of the company because it brings this just unbelievably valuable capability to the world. Not just safety, but freeing humans from the drudgery of driving cars around it's going to be a qualitative change in the way that people all over the world live their lives.
Yeah, definitely. It seems like, this is another angle, but the birth of Tesla was in the 2000s, that decade, but the birth of Tesla 2.0, or Tesla, the autonomous driving company, was last decade, and we're seeing the fruits of kind of this rebirth, a new birth of it's almost like I don't know, it just seems like it's not just obviously the electric vehicle company that was first imagined. It's on a trajectory for something much bigger, and I think that's going to be definitely an exciting thing this next decade.
It's fortune favors the prepared, and they've certainly been preparing.
Yeah, so. Exactly. All right, James, I'll go ahead and link to your Twitter bio in the video description, and probably to our last couple talks. We had some fun talks on Tesla Dojo supercomputer, if you're wanting some ideas on that. But this stuff is changing so fast too. It's like every month we have new information. So I think the best is just be in touch continuously with someone like you to give us updates. But thank you again, and we'll touch bases and do another show. All right, thanks, James. Bye.